There, recording begun, party has started. Happy Garbage Day, welcome back. We have 4 weeks of class left by my count, 3.5 after today, give or take, so we're in the home stretch here. I have formative assessment number 5 for us to talk about, which is, as you have noticed, a different animal relative to some of the earlier ones. Number 6 is up, which is your next thing to do. And we have not yet talked about the questions that are on number 6. So this is something I'm looking for you to complete probably after Thursday for the most part. But what you can start working on is homework 4. I put that up yesterday. This one, I would say, of all the homeworks, 4 is the hardest, actually, not 5. It's not hard because it's difficult, it's hard because it's complex. So homework 4 is a piecewise model based on a true story from a former student who was doing a dual PhD JD law degree and was talking about getting ready for the bar exam. So the story behind homework 4 is that it's a 3-piece study of students measuring stress before the exam as while it's approaching, right after you take it, and then while you wait for your scores to come back as 3 different sections of time. So that one is not due until after Thanksgiving, so you have plenty of time to work on that, but I wanted to let you know that it is available. So we can have fun with that one. But in the meantime, I would like to talk about the story problem that I gave you here. This is based on, I would say, an amalgam of several different designs that I've helped with over the years. And I had a chance to look through all of your answers this morning and update grades. And it looks like across all of you, you captured the majority of what I was looking for, but I wanted to go through each of this piece by piece and get your thoughts and questions, because this is the type of activity that eventually I would like us to all be able to do, to provide advice on what to do with the longitudinal data set, and also how to inform, based on what the models need to have in them, what the design might need to look like to be more, have a better chance of showing the effects that the researcher is interested in. So the story here, there are 25 people who are participating in some kind of weight loss program. This is meant to be pilot data for a bigger project, so we have 3 occasions. A baseline occasion, they go through some kind of 6-week program. They take a second occasion, and then they want to measure how well they're able to maintain weight loss, which was the goal of this program, for an additional 3rd occasion. So this person, as one does nowadays, didn't know what to do with this data, so they asked the Google, went to Google University to figure out how to run some sort of longitudinal model. And I made up code that in each of the packages, so you can look at the one that you're most familiar with, as to what a standard growth model would look like. And most of you identified right off the top, what kind of model would I say this is? Like if I were to use words to describe this code, what is this doing? Can I share my screen? You know what? That would be a wonderful idea, wouldn't it? I'm looking at formative assessment 5 though, so you can have your answers up as well. Thanks for the reminder. So what kind of model is this that this person stumbled into code for? What's it have in it? The rumors are quiet. Zoomers?
Sorry, I dropped my phone. A random intercept and a random slope.
Yep, so we've got, that's written explicitly here in the SAS code, a random intercept and a random slope. And it's also written explicitly with C dot occasion as a slope, not a set of dummy codes, but a slope in here. And then the same thing in R with occasion in 2 different places. And given, let's see, given the fact that this is one variable, what kind of random intercept slope model is this? What kind of change is this person going to get out of this code? What pattern? What shape? Looking for a word that starts with an L.
Linear.
Linear, yeah. So occasion is a variable that, as it says in the instructions, is 1 equals baseline, 2 equals the finish of the treatment portion of the study, and 3 is follow-up. So this person fit what I would call a random linear model of change, so fixed and random effects of occasion being treated as a continuous predictor. And I know that in the code because occasion is not on the class statement. I know that in Stata because it's C dot, and I know that in R because it's not a factor, obviously. You might have to check the data set, though, to make sure, but the intent is that it's being treated as a continuous variable. So yes, linear is the right answer. So given this code, then I asked a few different questions about what are some issues, first related to estimation. And I try to give you a hint. I can think of 2 issues that would apply to all 3 of these packages. So with estimation, what do you think about this person's code? What's it going to do? What estimator has this person selected first off? Yeah, ML. So this part here, method equals ML. ML as the keyword in Stata. By the way, older versions of Stata, this would be MLE instead. The XT mixed has it that way. And REML equals false, means it's going to be ML instead. And several of you noted a concern about maximum likelihood instead of REML. What's the concern there? What's going to happen as a result of using maximum likelihood as opposed to residual maximum likelihood?
To me, the problem here is that with maximum likelihood, we are not correcting the random effects variances and covariances based on the fixed effects used to estimate them. So in this case, maximum likelihood, and also based on the small sample size, those calculations will be smaller than should be.
Yes. So also noted in the chat window, the estimates of the random effect variances are going to be too small. The residual variance is going to be fine. It might be just a little bit off, but that's not where the problem is. It's random effect variances and covariances, when they're estimated in maximum likelihood, do not take into account the number of fixed effects that was needed to get to that amount of variance left over. So as a consequence of that, you can think of the numerator of variance as being like sums of squares. The denominator is n in regular maximum likelihood and n minus k for the number of fixed effects in REML. So if you divide by less, then you'll end up with an answer that is incorrect. So in REML, the variances are going to be bigger, which matters why, besides just getting an accurate estimate of variance. A few of you noted potential complications of this downstream. What happens if your variances are too small?
You have incorrect standard errors and p-values.
Yeah, the standard errors of the terms that go with them become too small. That's the consequence. So if we have, say, we haven't gotten to level 2 predictors yet, but you've seen examples of this with fixed effects. So if you have, say, a fixed slope, if the fixed slope has a random slope with it, its standard errors should get bigger than if it's fixed. And it doesn't get bigger enough, essentially, if it's using maximum likelihood. So you can end up with higher type 1 error rates, particularly in this case. And why is it a problem in this case? What feature of this person's data makes this a concern?
Sample size.
Sample size. So sample size at what level?
2.
2. At the highest level is where the concerns are. So even though this person has up to 75 data points, only 25 of them are across people, and that's where the random variances are across persons. So if this person had a study of 250 people, I'd be like, it's fine. It's probably not going to matter. But for something this small, the use of REML estimation does matter. And what goes along with that then also is the use of denominator degrees of freedom. So we added DDFM equals Satterthwaite in SAS, DF method equals Satterthwaite in Stata, and in Elmer, on the summary statement, it delivers the test of the fixed effects with Satterthwaite degrees of freedom as well. So the use of REML tends to go hand in hand with the use of denominator degrees of freedom. The use of ML instead tends to go with models that don't use denominator degrees of freedom, in which case all the fixed effects would be tested with z's or chi-squares rather than t's and f's. There's one more thing related to that is a potential problem in Stata, and actually if you try this combination in Stata, it won't run. You will get an error message, because in Stata you can only add denominator degrees of freedom if you're using REML. So that's one extra thing that Stata does differently than the other packages. So that's one issue, is the ML versus REML. So just to recap, REML matters when you have smaller level 2 samples to provide accurate random effect variances and covariances. Otherwise, if they are too small, then your standard errors are too small and your p-values are too small. So any questions on that point to start with? Okay, then in terms of my list here, 2 issues for all programs. We've done 1. The 4th for Stata alone was the not having degrees of freedom unless you have REML thing. There's another issue with respect to this specification, and I would call it either an estimation issue or a specification issue. What I'm looking for is the coding of this variable. It's coded 1, 2, 3. Now, is that wrong to do it that way? Ugh. By wrong meaning, like, would you come to a completely wrong set of answers if you have it coded 1, 2, 3 instead of something else? I would say no, it's not wrong, but it is weird. So in this linear model, so occasion is being treated as a quantitative predictor being given a linear slope. If it's coded 1, 2, 3, when is my intercept?
0.
0. What
Right.
time was that?
Prior baseline?
Well, if these are equal interval, which I intended them to be, so several of you commented on that, like, does 1, 2, 3 make sense? It only makes sense to code them that way if it was exactly the same amount of time, which I had intended. But if it's coded 1, 2, 3, then the intercept in this model is going to be 6 weeks before they even signed up for the study. Now, that's not wrong, but it's weird. Likewise, random intercept variance, then. You would also get differences between people 6 weeks before the study started. So when we get into level 2 predictors, which is starting on Thursday, my hope is to start talking about those, then we will predict individual differences in intercepts and slopes. And it doesn't make a whole lot of sense to predict individual differences in an extrapolation of data that don't exist in your current sample. So to me, that's a problem, because the model parameters aren't going to tell people what they meaningful values. Okay, how are we doing so far? So far, so good. Do we need to shut the door? Is it loud over back there? I can hear the conversation from here, so I'm guessing it's louder on the other side of the classroom. Thanks. All right, Zoomers, we're doing good? Yeah, there's a conversation happening outside the room that we're trying to avoid. Good. So those were the 2. There's a third regarding the code of SAS and Stata that is not a problem in R. Anybody know what I'm talking about? This is a subtle one. There is a piece of code missing deliberately.
Is it if you don't specify the covariance structure?
Yes, the covariance structure of the G matrix specifically. So normally on the random line, after the slash, there is type equals UN. And in Stata, it happens during this section of the code. I have, I think, cov type unstructured or something like that. Why that matters is without it, you do not get any covariances or correlations among your random effects. So the U's are considered independent by default, which is silly because the U's come from the same person. Why wouldn't they be related? In R Elmer, and I believe in LME as well, those random effect covariances are estimated directly as correlations, but they're always in there. You don't have to do anything special to get them, which is one nice thing. So without having covariances among the random effects for the same person, the model is potentially misspecified, which means you may not get the answers back that are optimal for your data. And these are the little pieces of things that I've had to learn over the years in teaching across packages. And I know it can get somewhat annoying or tedious to have the same thing 3 times, but It's a very different animal to learn how to do longitudinal analysis than to learn how to do it in this package, and this package, and this package, because you have to get to know sort of the nuances of what each does in its own way. So I've had to learn more about models and by using different packages, and then I have a chance to show when they do agree and when they don't agree across programs too, which is also something good to know. One of you asked about this subject thing here. So subject ID is what I used in this example. That's just any level 2 variable that denotes which subject is which. It can be any variable at all. I tend to use things like person ID or subject ID or family ID just as placeholder examples, but it can be anything. And one more thing some folks mentioned is with respect to the R matrix. So what kind of R matrix is being specified in each of these packages?
Independent?
Independent. So R matrix holds what again? Do a little vocabulary review. What's inside R?
Residual variances.
Yeah, level 1 E, residual variances and covariances. So normally that is controlled by a repeated statement in SAS, a residual statement in Stata, and in R it depends on what package you're in. If you don't write it, what you get by default is independent. So that says equal variance across time with no covariances. In SAS and Stata, you can change that to be something else if you want to, and you can test whether or not that improves model fit. In R Elmer, though, you cannot. There is no choice besides a independent R matrix. You'd have to switch to the NLME package, which has LME or GLS, which has choices for those instead. But with 3 occasions, I can tell you there's not going to be enough information to do both. You're not going to be able to estimate a random intercept variance and a random slope variance and some other stuff in the R matrix. It's too much to ask of the data in those cases. There was one more. I'm trying to remember what it was that I wanted to say about this one. I think that's it. Maybe, occasion should be on the class statement someone mentioned. That is only if it's being used in a repeated line to structure the R matrix. Otherwise, that would turn it into a categorical variable, which we want it to be a continuous variable. So in all of my examples, I have 2 different variables for time. One is treated as categorical and one is treated as continuous for that reason. Okay, that's question 1. Can you think of anything else that I'm forgetting? We've got more questions to go, so I'll ask that question at the end as well. All right, question 2? Yeah, go for it.
To me, in RStudio, it is weird to start with this kind of models because you have all of these components. So if you would like to know what part of the model is wrong, you couldn't know it immediately. So to me, it's better to start with a basic model. The empty means random intercept model, and then adding different components step by step and testing if they are helpful or not.
Yes, so just to repeat for the Zoomers, the comment was, this is just estimating one model and calling it good without testing each of the components or testing how well it fits, and I agree with you. But if you go and ask the internet, like, how do I fit a growth model, they will give you a model and walk you through it, and as if that is the end of the story. So this is meant to approximate, what you would get from well-intentioned searching as examples. They don't necessarily go through all of those steps, but I agree with you. You would want to build your model sequentially, carefully, paying attention to what needs to be included and what doesn't, or at the very least, you can start with the most complicated model and then subtract things from it and see if it makes it worse. So you don't necessarily have to go up, you could go down, but yeah, just fitting this and calling it good would not be a very careful strategy. I agree with that. But what about this model in the first place? That's question 2. Do you think this model is the right type of model to answer this person's questions, which is to remind you, they wanted to know how much weight did people lose and how were they able to maintain their weight loss? So, and they expect individual differences in both of those types of change, initial loss and subsequent maintenance. Does this model give them answers to those questions? What do you think? No.
I had concerns about being underpowered.
Oh, yeah.
Whole thing, communications and sample size of the participants.
Yes, I have those same concerns, but I'm going to put a pin in those and save those for question 3, which is how would you design the study differently? If she just has to work with the data that she has, sorry, I'm giving this person an identity, because like I'm in this role, right, where someone hands me a data set and is like, make it work. Okay, I would have done it differently, but since I wasn't there at the beginning, I got to make the data work. So given this person's questions and given this type of model, does this type of model answer these questions? Is my question to you. Most of you said no and came up with some variation of the same reason why. Zoomers? There's an answer. No, because the expected weight loss pattern is not linear. Yeah, this is a linear model, meaning that we would specify the amount of weight loss per unit time, even though the first unit time is from beginning the program to the end of the program, and the second unit time is from the end of the program to a subsequent follow-up occasion. So this is not a linear expected change. What would it be instead, potentially?
Piecewise.
Yeah, this is a piecewise model, because they have different questions about change during different periods. Did the program work is the difference between occasion 2 and occasion 1. Did weight loss get maintained is the difference between 3 and 2. And if weight loss got maintained, what should we see in a slope if you go from occasion 2 to 3? Yeah, no slope, right? Maintenance is like the definition of no change. So if you're, hang on, I got to do it backwards. This way, right? Does that look right? Weight loss and then maintenance would be this kind of piecewise model. So not linear because the study isn't designed that way. So yeah, several of you said, I think this could be a MANOVA model instead, and you're also right. A saturated means model is equivalent to a model that has an intercept and 2 slopes in this case. So just letting the 3 means be what they want will fit equivalently to putting in an intercept and 2 slopes. An intercept and 2 slopes allows you to test moderation. So like which participants were most successful in losing weight? Did it have to do with any of their baseline characteristics or anything else you measured about them? Which participants were most successful in maintaining weight loss? And how do we predict that? So that sort of 2-piece model sets up that kind of idea. So yeah, this is probably not going to fit the data unless not only did they lose weight, but they kept losing weight at the same rate after the program stopped. And that is probably not going to happen. It's easy to lose weight at first, but then you get hungry and you get tired of eating chicken and broccoli at every meal. Am I right? Yes. Question from the Zoomers, Carl.
Yeah, so I was thinking the piecewise model would be good as well. I just was curious, like if they responded to me and said, like, well, what about doing a log time model where it sort of goes down and then gets shallower? Would that represent the idea of change and then static?
I think it could, but with only 3 occasions, it would be hard to differentiate the fit of that relative to like a 2-piece model. You'd be spending 1 extra parameter that would account for any like deviation from that bend. So yeah, so like if the goal was just to capture this type of trajectory, log time could work for that, but it doesn't allow a direct answer to the question like, did they maintain weight loss? The answer to that question is the difference between occasions 2 and 3.
Okay, great. I see. Thank you.
Yeah. So it's a combination of what should the curve look like and what does the researcher want to know about the change over time. And this should be 2 different kinds of changes. What about the model for the variance? Can this person have 2 random slopes with only 3 occasions? Nope. You're out of degrees of freedom. So if they were to fit a piecewise model, they could either have the first piece be random or the second piece, but not both. So then an unstructured model or a compound symmetry heterogeneous model or something like that would probably be a better bet. So that would be my first advice to them. It's like, you need a different kind of model for this type of data. But then if this study is meant to inform a larger data collection effort, what types of design changes would you recommend? What about sample sizes?
Having a control group is what I was going to say first.
Yeah, well, that has nothing to do with the content of this class, but that you're absolutely right. If you want to be able to say that it's your program that is responsible for this weight loss pattern, you need something to compare it to. So either a true control group or some kind of treatment as usual or a waitlist control, something to serve as a comparison for what would have happened to these same types of people had you not intervened in their life. So that would be one thing. What about sample sizes? Do we need more people? Yeah, I think so. Do we need more occasions?
Oh, yeah.
Oh, yeah. So if I had to pick one, I would pick more occasions in this case. Several of you noted that you only can capture what kind of change during each period with the hand gestures here. What kind of change can you get with 2 points forming each section? My hands are straight. Yeah, linear. Do you think weight loss is linear? Probably not. So more occasions within persons would allow you to better estimate the change during each section or lack thereof, as well as nonlinear change. In a lot of instances, we might expect a lot of change initially and the rate of change to slow down, and this may be one of them. But any type of asymptote or nonlinearity of the function, we would need more occasions to capture. If we had, say, people measure themselves in 3 weeks, so they start the program, measure at 3 weeks, measure at 6, measure at 9, measure at 12. Then we would have 5 occasions. Then could we have 2 random slopes? Yeah, then we could have 2 random slopes. So we would be able to quantify individual differences during each phase, the extent to which they lost weight, the extent to which they maintained weight loss. In terms of power, though, more people allows more precision of the random effects variances. More people allows more power for the detection of effects of time invariant predictors, such as the difference between a control group and a treatment group. So if you want to have maximum power to show that your treatment works, what you're actually hypothesizing power for would be an interaction term. Group by change, specifically. Did people who got the weight loss treatment change differently than people who did not? That's a level 2 question. So more occasions on both sides, but I would pick more occasions before I would pick more people in this case. In practice, ways that you can decide which is relatively better would be doing power analysis via simulation. So you make up data with the patterns that you hope to find, and then you can play with the different sample sizes and see at what point the breakoff is in terms of when more isn't better. There are dedicated programs to do that to some extent, but simulation gives you the most flexibility and power. All right. I think that was, I made a list of all the things that I wanted to say. Let me refer to my list here. Oh, one more. I knew I was forgetting something. There was a comment about stata code, and another option that I usually type in here is the word variance. So depending on how old your stata package is, once upon a time it defaulted to showing standard deviations for the variances instead of variances. That was when I initially learned stata, I realized that it did that, and then I found the option by writing the word variance in here to make it show variances instead. So you just have to know what your package is defaulting to to override it. The same thing happens, by the way, in R. Where's the R code? In Elmer, I believe it shows variances in one column and standard deviations in the second, but in LME it shows standard deviations. Why? I don't know, because the people who programmed it decided they liked it better that way, or perhaps because it's more stable to estimate smaller numbers. But that would be another thing to watch for if the numbers don't agree across packages, is what are you getting? Are you getting variances or are you getting standard deviations? Variances is what I'm used to seeing, so that's what I usually ask for. All right. Questions or comments?
I have a question about
Yeah.
the number of slope for the piecewise model.
Mm-hmm.
I was thinking, since we have 3 events, which is before the treatment, during the treatment, and the follow-up, why do we have 2 slope piecewise rather than 3, such that we can compare the baseline slope with the treatment slope, and then the treatment slope with the follow-up slope?
So the question was, why do we only have 2 pieces instead of 3? And the way that I had intended this to read is that you only have 3 occasions. So there can only be 2 lines between 3 occasions. But that's another kind of design, though, that would potentially allow you to estimate 3 slopes, is if you took multiple observations during baseline. So like you had them measure for several weeks before they started the program. You would probably expect the slope to be flat in that case. Then multiple occasions during treatment, you could have another slope, and then multiple occasions after treatment stops before follow-up, like the last occasion, then you could have 3 slopes if you did it that way. And you would also potentially have 3 intercepts, depending on how you want to specify it. Because if you have occasions nested within, like, I'll call it phase, then you can almost think of it as multivariate across people, because just having occasions within one phase would be enough for a multi-level model. If you have 3 different sections with multiple observations, then that would be considered multivariate and multi-level at the same time. That would also be a better idea to be able to better characterize where people start in particular than just one occasion. So what did you think of this exercise? Did you like this?
Yeah.
Better than memorizing things?
More challenging.
More challenging, yeah. So what I hope to be able to do in terms of what's the content that we have left is spend a few more classes with some examples like this, where we can kind of talk through, here's the design, here's what they want to know, like what would the model look like, and what would be the steps, and what would be the things to watch out for. I hope that we have some time to do that. That's my intent, so that you can start transitioning into this role of being able to decide what needs to be done, not just doing it as you're told. Yes?
Yeah. I know that in this example and in most of the models we are doing now in this class, we assume that the R matrix has an independent structure, which means the same variance across time.
Mm-hmm.
Within person variance is the same.
Yes.
But then in the V matrix, when we combine the G matrix and the R matrix, we have different variances and covariances.
Mm-hmm.
My question is, doing that, are we allowing within person differences or variance, or we are only assuming that between person variability exists over time and between persons?
Okay, let me try to make sure that I can understand your question and also rephrase it for the Zoomers. So usually, yes, the R matrix that we specify has equal variance across time and usually no covariance across time. And when you combine that R matrix with a V matrix that has any kind of random slope in it, the composite marginal put back together again, V, I'm all about the hand gestures today. The V matrix does have heterogeneity of variance and covariance over time. But what it's saying is that the cause of that heterogeneity is between person differences in within person change.
Okay.
So that is a testable assumption. But the problem that comes in with this type of software, your choices for R matrices with respect to the variances is either they're all the same or they're all different. And if you let them all be different, that is trying to capitalize on the same thing that the random slopes are trying to do. They're both trying to capture changing variances over time at the same time, so they can compete with one another. One of the benefits of switching to either like a software package where you control everything, like NL mixed or Bayesian, like STAN, that kind of stuff, where you have to write out every aspect of the model so you have total flexibility. You could look at the residuals and be like, occasion 2 needs a little more variance than the others. I'm just going to let occasion 2 have more, and just sort of, customize it as you need to, as opposed to let them all be different. Who cares? And you can do that in SEM software quite easily as well. So it is an assumption, but if you try to do both random slopes and heterogeneous residuals, both of those things are trying to capture the same phenomenon at once, and they're going to fight against each other to do so. Where different R matrices in terms of the covariances tends to be most useful is either when you don't have a random slope in the model, like fluctuation types of data, because compound symmetry in terms of the covariance pattern is probably not reasonable in that case. Occasions that are closer together are going to have a stronger covariance. Or if you have a lot of data, like 50 occasions per person, and you fit some kind of random slope model, there's probably still residual correlation left over, like in a time series kind of approach. So does that help?
Yeah.
Okay. Other questions, things you want to talk about? Otherwise, the rest of today is kind of meant as a review to get us ready to head into predictor land. All right, Zoomers, you still with me? Thumbs? Thank you. All right. Then I will shut this down and turn this on. So this is lecture 7A. It's a little one. It's only 15 slides. This is meant to be just a recap of what we've done so far and what would be all of the steps that our researcher would skip, essentially, in heading straight to the random linear model. What I would do in practice, decision points and whatnot. So this is lecture 7A. Each of these steps we'll go over one by one. So first thing, always empty means random intercept model. Always. Doesn't matter if you have unbalanced time, doesn't matter if you have equal intervals or not, you can always estimate this. The reason that I always start with this is that it tells you if you even have longitudinal data in the first place. I also do this for any predictor that I'm not sure if it's time varying or person level. So interclass correlations can be used to diagnose at what levels any variable has variability across time, across persons, and across any higher levels as well. So interclass correlation then is between over total, where at this point we are assuming heterogeneity is not in the data, right? This is a homogeneous variance model. So we know this is probably not going to be right, but it is something to start from as a baseline. So interclass correlation, you can think of it a couple different ways. You can think of it as the proportion of variance that's due to between person mean differences specifically. Just intercept is mean differences. You can think of it as the average correlation of occasions from the same person, and that you would see in the V-core matrix when it's R and G are put back together again. And as the answer to a few different questions in your homework, and more to follow, the interclass correlation is an effect size. We can always do a likelihood ratio test to judge whether we need a random intercept variance in the model versus just a residual, but the interclass correlation tells us how much the random intercept variance is contributing to the data. So this is one way to answer the question, do you even need a multi-level model in the first place? How much of the data is at level 2 as opposed to level 1? Only when it's 0 and stays 0, no matter what you do, is the answer you don't need a multi-level model. That's very, very rare, if ever. This also tells us, in terms of the outcome, where predictors have the most potential impact. So if I have an interclass correlation, say, of 0.3, how would I describe the relative amount of variability of between versus within? Which is more if my interclass correlation is 0.3? Within. And is that level 1 or level 2? 1. So on your next homework, I'm going to have some drop-down menus, questions for interpreting these things, and some of them are going to be logically inconsistent. So you will have to choose between things like level 2 within, level 1 between, level 2 between, or level 1 within. So watch for those. I'm looking at, that's a vocabulary drill. So if interclass correlation is 0.3, then it's 30% between, 70% within. That means that time-varying predictors are going to have more to do than time-invariant predictors. If most of the variability is at level 1 over time, we need over time things to capture that. If most of the variability is across persons, then we need person characteristics to capture that. But this model doesn't have anything to do with change over time in it, which is another way that people can differ from each other. But this is a starting point. Next, in thinking about change over time, you got to figure out what time is. What I tend to do almost always, and what you've only seen in this class thus far, is occasion of study as time. So how long has it been since you were first measured? That's time. It can never be wrong, is why I prefer it, because it's purely a within-person metrics. Relative to where you started, how much further is it now? Some alternatives, though, that you may see, particularly in accelerated designs. So an accelerated design is when people start out at different places in time, and then they're measured over time too. So if I grabbed a sample of older adults who started between the ages of 50 and 80, and I measured them all for 5 years, then if I just put in the age they are at each occasion, that would be lumping together all the sources of variability between people who were started out 30 years apart with all the sources of variability that were introduced in following them over time. Those are two different things. So these types of accelerated designs, when you have age as time or grade as time or distance to and from an event, those require more complex models to be able to pull apart what are cross-sectional differences that were there to begin with from what are longitudinal differences you've introduced by following them repeatedly. This will probably be one of the units in the advanced class, just at least one example on this or so. And in every case, we want to use exact time. So if people don't show up exactly when they're supposed to, then it's not time 1, 2, 3, 4. It might be time 0.9, 1.6, 2.8, like whatever distance in time it is, you can have continuous time in these models, and you should. Otherwise, if you're rounding time into convenient integers, you're introducing measurement error, and we don't want to do that. Decide on where time 0 is going to be. So this is a decision where there's not a wrong answer, but there are plenty of weird ones. The question is, at what point in time do you want a snapshot of individual differences in the amount of an outcome that you can then later capture with person-level predictors? So do you want to put time 0 at the beginning and put in a predictor, let's say, treatment group, treatment versus control? Then there should be no group difference at time 0 because it's the beginning. If you put time 0 at the end, then you should see a group difference because at the end of the study, the groups should have diverged. I'd say the weirdest answer that you can do is to forget about centering time and leave it uncentered to where 0 is not even in the study. Not only is that weird, that can cause estimation problems. So I think I told this story either in this class or in the workshops that I gave this summer. If you've heard it before, I apologize. I once had somebody fit a very, very complicated multi-level structural equation model to longitudinal data, and it was data on older adults. And one of the parameters in the model was age. And the model was blowing up. Couldn't get it to estimate. She sent me the code. Do you know why it's broken? Yes, I do. Because you're trying to estimate intercept differences across newborns from data collected from people in their 80s. That's why it's broken. It couldn't come up with it. It's too far away from the data. So that becomes wrong, right? Because you come to the conclusion that your model isn't viable when in fact it's the parameterization of it that isn't viable. So time zero, somewhere in the data. As you've seen, what happens if you center it so that time zero is the beginning, and then you become interested in time 3? Could you ask for predictions at time 3? Absolutely. So you could ask for what the intercept would have been at time 3, what the linear slope would have been at time 3, what the prediction of individual differences would have been at time 3. You can get any other time as linear combinations of the model fixed effects. So that's estimate in SAS, lincom in Stata, and contest 1D or GLHT in R. So we can always get it for the other times. Next, figure out what you're trying to model. So this is description time, only it's description with another model rather than the observed means. So we would want to estimate a saturated means model. If you have balanced time, you can do that directly. So what you would do is take your time variable, turn it into a categorical predictor or a factor variable, and then get a separate dummy code basically for each other occasion relative to a reference occasion. So if I had 6 occasions, a saturated means model would give me an intercept and 5 mean differences. If time is not balanced, I would temporarily round time into intervals just to get this model and make a picture with it, but I would not keep that rounded variable. The variance side, if possible, I don't have a slide on that. The variance side, if possible, should be unstructured. If you have unbalanced time, though, you can't have unstructured, but you can always have a random intercept if nothing else. Now, why it matters that you get the means that you're trying to capture from a model versus the data. It matters if you have incomplete data. So if I just run descriptives on my data set, I can get what the mean is at time 1, at time 2, at time 3, right? No problem. But what if not everybody came back? The mean from the observed data at time 3 is probably not a random subsample of the people you started with, right? People quit or drop out of research for reasons. Children move, old people die, dieters get tired of eating chicken and broccoli and quit your study. There's reasons, right? So to the extent that people don't come back for reasons, the mean at the later occasions is not a good estimate of what it should be. What the saturated means model tries to recreate is what would the means have been had your data been complete. So it's trying to extrapolate or interpolate essentially across what there should have been there, under an assumption of missing at random, which means random conditionally, considering the other data you do have, whereas the observed means are missing completely at random. So this is why if you're going to do like a table of descriptives, which is a common thing in manuscripts, I would give the saturated means, not the original ones. Giving the original ones can cause discrepancies where your trajectory would look like it doesn't match, but it doesn't match for a reason. Okay, questions or comments on that? The reason to get the means is to make a picture. What kind of trajectory do you see? Is it flat or not flat? Is it bendy or straight? Is it continuous or discontinuous? Each of those answers is going to point you towards a family of models that's going to be most useful. Now, what if you have no change? I have here a continuum of study intent and study result here, because longitudinal research isn't always about measuring change. Sometimes it's about capturing within-person fluctuation and associations, things like stress and mood and heart rate and social support and all kinds of things that may vary from day to day, but they don't change systematically. So on one end is the idea of pure within-person fluctuation, where time is irrelevant. So if you have, say, intensive longitudinal data, like you have people answer questions multiple times across weeks, but you're not doing anything to them and you're studying something that shouldn't change, you may not need any effects of time in your model for the means. Your model for the variance might have a random intercept for it to control for the fact that some people are just higher or lower than others, and then maybe some kind of covariant structure like autoregressive or Topolits or something like that in the R matrix. On the other end, on the right-hand side this time, is a prototypical growth modeling study where you expect people to change and you've sampled time to allow enough time in between occasions for them to have changed. So in that case, yeah, fixed slopes for change over time. They could be linear, quadratic, piecewise, log time, exponential, all kinds of choices there. And then potentially random versions of each that would allow individual differences and simultaneously allow variance heterogeneity. So these are the easy cases. But sometimes you end up in the middle. Sometimes you end up with, I'm going to study growth, and you plot the means and they're flat. People don't grow. Well, the question would be, is it just on average that they're flat, or is there no individual change? So in that case, you might still start over here. You might have a fixed slope that's 0, but still have random slopes in the data. Or you could be in a situation where you didn't think time should matter, but it does. So I know I told this story before, but just to make the point of when that could happen, there was a daily diary type of study where people got phone calls every night to collect data. And one of the questions was, did anything stressful happen today? And if you said yes, you got 10 minutes of follow-up questions about what happened to you. If you said no, you got off the phone. By the end of the study, people had figured this out, and they're like, nope, I'm good, thanks. And you see this miraculous decline in stress across the days of the week that had nothing to do with actual change and everything to do with artifactual change. So in that case, you would still want to model change in stress across time because you're capturing this measurement reactivity process, which could still contaminate your data with respect to the things you do care about. So design and intent can inform which models are going to be most useful, but not always. So doing data description via saturated means, via pictures, via growth trajectory pictures, all of that stuff is going to be important. All right. Thoughts or questions? All right. Here's an example, another story. This is a true story. So this was a student who was sampling college students and their intent to drink each week. So this is before daily diary studies were really a thing, intensive longitudinal data. So these are the individual trajectories, right? They're all over the place. There's a bunch of people, these are college, freshmen, sophomores, juniors, a bunch of people who are not planning on drinking a whole lot. Some people who are planning on going nuts, right? 50 drinks a week, I think, might kill me if I tried that. So do not try this at home. And this was the plot of her saturated means across time. So initially we looked at this and we're like, well, it kind of looks like maybe a 3-piece model, maybe 4, maybe kind of quadratic-y, like here's it goes up and it comes back down. And this was a psychology student. And as a psychologist, I'm allowed to say this, psychologists are very good at looking up data and coming up with a reason after the fact as to why it must have happened. And so we thought, well, maybe as the semester goes on, the students are more stressed and they're planning on, partying on the weekends to make themselves feel better and Nope. She dug through her data a little more carefully and realized that they had started the study with 3 different cohorts as to when week 1 was. For one group, week 1 was 1. The next cohort started at week 2. The next started at week 3. And what you're seeing in here is when spring break was. When you realign the data relative to spring break, you get this. The noise simplifies pretty readily into a giant spike that says, these are the kids who are going crazy on spring break, and then here's the rest of the time. So the plot on the bottom is the means off a week or so based on the x-axis, but this is what it looked like. So this requires a completely different strategy to model change over time than what this pseudo-quadratic-y strategy would imply. This quadratic-y curve is a misalignment of people relative to a critical event. Now, two things are of note here. The first is that this student did not expect the number of planned drinks to change systematically over time. This was supposed to be a fluctuation study where they were going to look at, students' friendships and relationships and their grades and their stress and their drinking is like this whole, the word is sequela, I think. Did I say that right? That's another word that I've only read in books, but I've never heard someone say out loud. But it means like stuff, like collection of stuff. It's a nicer way of saying that, sequela. No, there was a systematic effective time in here, spring break versus not. Now, one could view this as a nuisance, or one could view this as an opportunity. So how would you think that this type of growth trajectory could be modeled? Any ideas? Piecewise. Yeah. How about just dummy code? Is it spring break or not?
Yeah.
Right? The end. So that's one dummy code. Now, if I modeled a fixed effect of spring break week, that would allow a mean difference between occasions where it wasn't spring break and occasions where it was. Yeah, I've lost my power of speech today. You'll have to forgive me. So that would capture the fact that when it's not spring break, people are planning to drink 7 drinks on average, and when it is, they're planning to double that. Now, beyond a fixed effect of spring break, what else could we have?
Random intercepts, random slope.
Yeah, random intercept and random slope. Now, can I have a random slope of a dummy code?
No,
You don't think so?
because here we will have just 2 groups, right?
Well, we have like 10 occasions.
Also, yeah.
Yeah, I can have a random slope of a dummy code. Now, what would it mean? If a fixed slope captures how much more crazy the kids are planning to go on average, ... Zoomers, you can play too. What would a random slope capture? Has no one here been on spring break before? In my experience, there were 2 kinds of spring breaks in college. The people whose parents paid to send them to Cabo, and the rest of us who picked up extra hours at our jobs to make up for the fact that half the staff was gone on vacation. So when I put it like that, what could a random slope of spring break mean or imply?
The variation between people.
Yeah. The variation between people in how much crazier they plan to go. So do you think that that might be an individual difference worth predicting? Who's likely to go nuts and who's not? Or the extent to which, if we view it as continuously? For the record, I did not go to Cabo. I worked extra that week, every time. I've never been to Cabo. Someday, maybe. But yeah, so then she was able to characterize 2 different ways in which these college students differed from each other. The intercept captured differences in sort of regular drinking. Some kids drink more than others. Yeah, that's the Zoom window. And then some kids go more crazy than others on spring break. 2 different types of individual differences. So this wasn't supposed to be a change over time, but it was. So this was an accidental one. Here's another one. This is a plot of means from what is known as a measurement burst study. I have this was from a conference presentation many years ago, but I really liked it and asked to steal it. So this is Rob Stosky and Marty Slawinski, who at the time were at Syracuse University. A measurement burst study is a type of design that combines fluctuation and change. So what this was older adults who were measured 6 times over a 2-week period. So burst 1 is actually the data that we've been playing with all through example 6, the 6 sessions of response time. They repeated that set of 6 assessments at 6-month intervals. And so there's 30 occasions in all, grouped in sets of 6, so that each set of 6 can examine variation, but then you can look at changes across the 6 as long-term change. And this was a measure of negative affect, and we can see 2 distinct types of time trends here. One is that within the bursts here, it looks like negative affect has a negative slope in every single one of these. That was explained as reactivity, because in the context of this study, what it was older adults who lived in a nursing home. And to be part of the study, they had some nice young person come to their room and talk to them and ask them questions and visit with them. And over the course of 6 visits, they got to know the testers, and they'd like bake them cookies, and it was like they were friends. And this was the hypothesis anyway. Negative affect decreased during each of these measures, in part because of positive reactivity to the measurement process here. But at the same time, if you look at what the mean is within each of these bursts, negative affect is getting worse over time. So when you think of something like negative affect, that is a prototypical example of a type of construct that's not supposed to change, right? Some people are grumpier than others, some days are worse than others, but here's 2 different kinds of changes at the same time. Now, we haven't seen an example of this, but I'm going to ask the question anyway. How do you think I should model something like that? Is time within person going to cut it? Would a standard 2-level occasions nested in persons kind of growth model cut it for this? Cut it means be sufficient. More likely, the 6 occasions that come from the same burst are more alike, and bursts that come from the same person are more alike. So this would actually be a 3-level model. It would be occasions within bursts, bursts within people as your levels, and the second half of chapter 10 in my textbook covers this type of example. So this would be a 3-level model with 2 different types of time, some kind of perhaps negative slope for change within a burst, and a positive slope for mean change across the burst as well as potential differences in variance. It could be that negative affect becomes more variable as people age, in addition to getting worse. So, point of the story, whether or not you think that you may have systematic change, your data will tell you for sure. So we would always want to go through the process potentially of thinking about what time is in relation to the construct that we're measuring change in, and then fit different types of models. So the type of change and the type of construct is going to guide you towards these different choices, but within that you can test, variations on the same theme. Anytime you're testing model parameters that are fixed effects, you can stare at the p-values. Anytime that you're adding individual differences via random effects or any kind of residual correlations, you can do likelihood ratio tests to see if it helps. Preferably using REML. Using maximum likelihood is okay if you have big enough sample size. So then we end up in this sort of situation where we have 2 different types of variability across people at a minimum, intercept differences and change over time differences. There could be multiple types of slopes, so linears and quadratics, early piece, later piece, what have you. And person level 2 predictors would predict individual differences in random effects. Level 1 then is residual, why are you off your line today? That requires time varying predictors. So what we have for the rest of this semester is focusing on level 2. How do we add person level predictors of why do people have different intercepts? Why do people have different slopes? If you are in the truly variation camp where there's no change, then you'd want to focus more on what should your R matrix look like? What kind of correlation pattern is in there? And is a random intercept sufficient, or do you need something else as well? In that case, you could end up in one of 2 different places with respect to the variability being modeled. You could have a random intercept in G and have some kind of residual structure in R, in which case you do have a demarcation of level 2 versus level 1. Or you could stay in the combined structures where there's no G. So then you might have different total variances, different total covariances. So long as you've adequately modeled whatever pattern of correlation there is across occasions from the same person, you're good to go. So then here's why it is, what, week 11 of the semester, week 12, something like that, and we're just now starting to talk about predictors. Here's my reasoning. The fixed effects are the center of the random effects. So describing what happens on average is the first step to figuring out individual differences in what happens with respect to time. Those random effects, then the variability of them across people, are types of outcomes within the model to be predicted. So if people don't differ in their slopes, you can't have predictors of slope differences have anything to do. So what types of random effects you have logically constrain what your level 2 predictors have to do. Fixed effects of time-varying predictors then are supposed to take care of what's left. So after you give each person their own growth curve, you predict differences between growth curves as a function of differences between people, then the E's are sort of still there to soak up whatever's left, and that's what your time-varying predictor's for. So all of the effects that you care about with respect to longitudinal variables as predictors are predicated on having time appropriately captured by the model. So we always take care of time first. And that's why this class has spent all of the semester on just time. It's the most important design effect that you can have. And if you don't get that right, everything that follows is going to be some shade of wrong. This is the part that you get to skip in the context of clustered data. So next fall, fall 2023, I'm teaching the clustered version of multi-level models. And that means that we're going to do like week 1 and skip all the way to week 12 relative to this class. Because if you have people nested in groups, there is no R matrix. There is no random time stuff, right? You just get to go straight to predictors. So this is the part that makes longitudinal data unique, is modeling change over time, individual differences in change over time, residual covariances in addition to that. All right, so then just 2 more slides to remind you what the steps might be to go through polynomial models or piecewise models. You can start at any point and go up or down the ladder, but I would test fixed and random effects separately in each step as well. Ta-da! All right, questions? Any comments or questions before we call it a day? No, everyone's tired. It's only Tuesday. You have a question?
Yeah, I have one, because in the book chapter 7, almost at the end of the book chapter, you mentioned that there are some assumptions that we have for each level of the model. Normality, independence, and homogeneity of variance, right?
Basically.
Those 3 for each level.
So assumptions that we would make is basically, the way that you can summarize them is that you are assuming your model is right.
Okay.
So if your model says you have homogeneous variances, that's your assumption. If your model says no, your variance increases quadratically over time because you put a linear slope in, that's your assumption.
Okay.
So most of them are testable as additions or subtractions to the model to make it fit better, and if it doesn't fit better, then you're probably good. Some of them are not. So like independence across persons, I don't know of a way to really test for that, other than to think of what are the reasons why some people would be more related, and if I put those reasons in the model, does it help?
Good.
Right. Other questions? All right, then since it is garbage day, that means I will say see you Thursday. Office hours tomorrow if anybody wants to chat. Otherwise, you can start working on homework 4 and formative assessment 6. No, 5. No, 6. What's next? 6?
6, I think.
6. All right, there it is. All right, thanks for being here, folks. See you on the other side. Bye, Zoomers.